Good evening, guys. Good evening, guys. Hi, hi. Hello, how are you? Hey. Can you see the scene, guys? Good evening, good evening. Uh yep. So hi, hi. Shankadip Chakravarti, good evening. Okay, so I will come back to you just a minute. Okay, great. So let's start. I'm waiting for the students to join. Just wait a minute, okay? Good evening, good evening. Okay, good. So we have easy problems today, and we will start with an easy one. So can all of you see the problem number one, guys, on the board? So let's take problem number one. Let's dedicate the board, next board to it. Okay, so problem number one. Problem number one asks following. It asks you that for some, oops, I'm so sorry. Yeah, for some real number a and b, you know, yeah, very good. So for some real number a and b, the following equation, 8x cubed plus 4ax squared plus 2b plus a is equal to 0 has three distinct positive roots. Okay, so if the sum of the base of two logarithms, base two logarithms, of the root is 5, then what is the value of a? Okay, that is the question. Okay. So let's try to write it down. 1 second. So this is sort of an application of, yeah, you're right, Shubham. Okay, so it's sort of an application of Vieta's formula, okay, and some basic ideas of logarithm. So what does it tell you? It tells you the following. Suppose R1, R2, R3 are the roots, of an equation, and the equation and the tech we are doing sum of logarithms, right? Base 2 log base 2 plus log base 2 R3. By the application logarithm, log of a plus log of b is equal to log of AB. From this result, we get this log of 2 R1, R2, R3. So how many guys don't know about log, guys? Who don't know about log? Tell me. Yes, but people even don't know about log. I will just repeat. I will just do the basics of log. Okay. Okay, sure. So what is log, guys? Log is very simple. So let's take it. Oh, you may not know e to the power x. Okay, let's say 2 to the power x. So here it's 2 to the power x. So 2 to the power x is equal to 2 to the some y is equal to x. 2 to the power y is equal to some x. The value of y for which 2 to the power y is equal to x is defined as log base 2x. Okay. The value of y for which, for example, 2 to the power y is equal to 3. The value of 3 for which 2 to the power y is equal to 3, it's called log 3 base 2, that is equal to y. So this is the definition of log. Now understand very carefully. So this is the definition of log. So understand that understand this thing. So let's take log. So log a base 2 plus log b base 2. What do you know about this? It's same as 2 to the power log a base 2 times 2 to the power log b base 2 by property of powers. So now 2 to the power log a base 2 is what? Is equal to a, right? 2 to the power log a, just see this, 2 to the power x. So this is the idea. 2 to the power y is equal to x means that y is equal to the x base 2. So therefore 2 to the power log a base 2 means it's equal to a times b, right? So therefore what do we get? We get that ab is equal to 2 to the power log a plus log b base 2. Now what is ab? ab can be written as 2 to the power log ab base 2, right? So therefore what happens? That this is equal to this power. So therefore we get that log a base 2 plus log b base 2 is equal to log ab base 2. Okay, and if you repeat this thrice, you get log r1 base 2 plus log r2 base 2 plus log r3 base 2 is equal to log r1 r2 r3 base 2. Okay, did you understand, guys? Olivia and others, who didn't, Olivia, Abhiram and air clashes. I don't know who is this guy, but did you understand this, guys? Did you understand this? What is the property of log? Now, if this is the property of log, and I hope you know about Vieta's formula, in this case, then what will happen is the following. Is that, therefore, what do we know about this? So let's go back to the first. So let's go back here. So therefore, what do we get? We know by Vieta's formula that a by 8 minus of a by 8 is equal to product of the roots, right? And sum of the a base 2 logarithms of the roots is 5. That is log of r1 r2 r3 base 2 is equal to 5, right? So therefore what do we get? We get that log, if you take log on this side, log of minus a by 2 8 base 2 is equal to log of r1 r2 base 2, that is equal to 5. So therefore what do we get? We get that minus 8 by, now if you take 2 to the power of this, that is 2 to the power log of this, is it turns out to be left hand side will turn out to be minus a by 8 is equal to 2 to the power 5. Therefore what do we get? We get that a is equal to minus 2 to the power 8. That is equal to what? That is equal to 256. Minus 256. That's it. Okay, guys? Um, no, Mukund, I cannot really speak in Hindi. I wish and I could. AMC, IMC, and AOQM is very good. Okay, okay, very good. Okay, so let's move on to the next problem. This is a very easier problem, relatively. Now let's move on to the next problem. Next problem. So let's go back to this problem. Yeah, Alf. So may I know, Alf, Aaron, Kokin, where you from? I mean, it will be helpful for me to know your. I mean, are you from India or from other places? Okay, so problem two. It's a probability problem. So each face of a cube is either painted red or blue, you know, each with probability half. So each face of a cube is either painted red or blue, each with probability half. Now the color of each face is determined independently. What is the probability? What is the probability that the painted cube can be placed on a horizontal surface so that all the four vertical faces are of the same color? Interesting. All the four vertical faces are of the same color. Okay, go ahead. So, what do you think? No, I'm a pure Bengali from Kolkata. You know, very good, Tanay. Don't give the spoilers for your friends. Don't give the spoilers for your friends. Nice, Mukund. Okay, so wow. See what the teacher of? Okay, so the idea is that each face. Yep, this is a bit easy. The harder problem will come soon. Oh, nice, Mukund. Okay, so each face is painted either red or blue, each with probability half. The color of each face is determined independently. What is the probability the painted face? So it's okay. We'll slowly get to know this. Don't worry, Mukund. Just see and how I am doing and approaching the problem. Okay, and you have to be good with a bit more. Uh, I mean, accustomed with English. I understand, but yeah, not half, but um, it's okay. Let's see what is there for you. So, how will you approach this problem, guys? Imagine. So, how many possible colorings are there for the cube? Tell me. How many possible colorings are there for the cube? How many possible colorings are there for the cube? That's a simple question. How many possible colorings? Yes. 64. 64, right. So 64 possible colorings. Very good. So now, it's sort of, you can understand it like this. It's sort of, okay. Very good. So 64 possible colorings are there. Perfect. So now understand this very carefully. Now, um, now consider that color. Okay. Consider that color which appears with the greater frequencies. Okay. I mean, there are 6 colors, right, on a cube. Two colors with 6 possible choices. So consider the greater color which appear, with greater frequency. Consider the color which appears with greater frequency. You understand? So what will happen? Yep. 64 without rotation. Perfect. You're right. But suppose, um, rather the question is interesting in the aspect that, okay, anyway, so now consider this aspect. So consider that there are 6 colors, right? I mean, 6 of 2 colors consists of 2 colors, right? There are 6 faces and 2 colors are possible. So consider that which is which occurs in higher frequency. Alper and Kokin, we are from Germany, I guess. Yeah. So guys, tell me. So what is the one? What is the possible arrangement of a greater frequency? What is the possible arrangement of a greater frequency? So observe that 4 colors will be actually same, right? Understand this? So understand this very carefully. So consider a cube. Consider a cube already placed on the floor. Okay. Now try to understand that what are the possible colorings over here. 2 colorings. Now it's 32, right? Now what are the possible colorings above? This has 2 possible colorings, but this has how many possible colorings? Either how many colorings possible, guys? Okay, you're from okay. Very good. Okay, so Sauradeep is suggesting us to take 3 cases. Okay, so yeah, go ahead. 3 by 32 is not the answer. Let's see what is the answer. I mean, you can count blindly, so you can count blindly. I mean, all the possible cases. Can you count that in a possible way? It's a combinatorics counting problem rather than more of a less of a probability problem, more of a counting problem. So 2 to the power 6 colorings are there. 2 to the power 6 is 64, right? Yeah. So understand that when it is possible, 5 colors exactly. So 6 colors, 6 face same colored. 6 face same color. 5 face same color. 4 face same color. Understand that 3 face same color will not occur because the vertical 4 are same colored. Okay, so it will not happen. So only 3 possible cases are there. Perfect, Sauradeep. Perfect. So now, what will you do? 3 by 8. No, not 3 by 8. Let's see. Now, Sauradeep, what do you think? Hi Lane Braj, how are you? Okay, so now understand this way: six faces of same color, right? Six faces of same color, and then how is it possible? Exactly two ways, right? Two colors, two ways, right? Two colors and two ways. Five by 16 is a good one, Ryan. Perfect. Now tell me the five faces same color case when it's possible. When it's possible, really. Five faces same color. So five faces same color. Is it always possible for five faces same color to have what is the chance when it will actually occur? So five faces same color. Try to understand the question very clearly. Okay, it's telling that given a possible arrangement, the painted cube can be placed. I mean, you can select which face to keep it downward. Try to understand this very carefully. You can select which face to keep downwards. Okay, you can select that. You understand, right? So that's the most beautiful part. So observe that if five faces same color, you just put the face that is not the same color on the bottom. So therefore, for five faces same color also, the same thing will happen, right? For five faces same color, the same thing will happen, right? So there are also two possible cases, right? Not 65. Why 65, Sauradip? I mean, see, we are not seeing the colors arrangement. We are just seeing the color. I mean, we cannot distinguish the cube, right, after coloring. Oh no, I'm so sorry. I think I'm doing some mistake. Yeah, I think Sauradip is correct. Oh, I think Sauradip is correct. Yeah. So it's 65. Yeah, 65 will come up because we will select. Yeah, you're right. You're right. So 65 will come up. 65 into 2. Yep, you're right, Sauradip. So yeah, 65 into 2. Right, you're perfect. So 65 into 2, that is 12 over here. And 2 over here. So why 65? Because we're selecting those five faces which will be same colored. And there are two possible choices for the same color. Red or green. Green or red or blue, I guess. So therefore 65 into 2 for the possible choices. Now let's take a case when four faces colored are there. Four face same color. So four face same color, how many way it can be done? It can be done in that case, right? Four face same color. So 64, we are doing it. 64 times what? So then the rest of the two is same color, so it doesn't matter, into 2 again, right? It's sort of 66 actually here. So therefore, what's happening over here? 64 means 62. 62 means 15 into 13, right? Sure, I will explain. Sure, I will explain. But observe that these six possible, yeah, sure, I will explain. But observe that for the six possible colors, it will not happen actually. You understand? For the six possible, all the four faces colored, for example, it can be colored in this manner. For example, let's take this example, guys. I will surely repeat the problem, okay? Don't worry. So, observe this. This one is colored. This one is colored. this one is colored, and say, so essentially understand for that corresponding face to occur, there will be this only round, I mean only the 4 vertical faces must be colored, right? Any deviation in the arrangement of that color, it will not happen. So try to understand this, that this is not the answer for the 4 colored face. Try to understand therefore what are the possible choices. So therefore what we select is that we select the vertical 2, the top 2, which we are not coloring. So we are actually selecting 6. I mean, we are the top 2 we are selecting, okay? So 6C2 we are selecting. Or is it? Not all the 4 colors will be selected, I understand. Or the all 4 faces. So what we are exactly selecting? So we are selecting, there are how many opposite faces? 6 opposite faces, right? So 6 opposite faces into 2 actually. Or is it? Is it 2? No, not 62. Yeah, try to understand this very carefully. Try to understand this very carefully. We can color such that the vertical positions, so vertical, the 2 faces are opposite, okay? We can color the same, only the 2 faces are opposite. That's the idea. I mean, so consider 4 colors, 4 faces of same color and another 2 faces of another color, okay? So try to understand, we will only select the opposite 2 faces, you know. So 3 are there, not 6, 3 are there. So it's a pairs, right? So 3 are there. So 3 pairs are there. Now 3 pairs are there, perfect, and 2 for each 2 colors. So it's 6, not 30. Okay. So 2 we are selecting these 2 pairs, okay? Because that's only when we get there are vertical connections, vertical same color, okay? Vertical 4 faces same color. So essentially what is coming up? 2 plus 12 plus 6, that is what? 30, right? And how many total possible cases are there? Or is it 30 or 20? I'm so sorry. So 20 by 2 to the power 6, which is same as 4, 5 2 to the power 4, that is 16. So 5 by 16 is the answer. All of you understood it? Okay, now I'll repeat this problem again. So coming back to you, Ilana Brej Doubt. Ilana Brej, I hope I spelled the name correctly. May I know where you're from? So I will repeat it for Ilana. I'm not sure. And I spelled the name correctly or not, but still, I will repeat it for the person. Okay. So problem 2. Each face is, so this is the problem 2. Okay. Each face is colored red or blue. Okay. With each probability to 1 by 2. That means the color of each possible face is determined independently. Okay. So what is the probability that the painted cube can be placed on horizontal surface so that the 4 vertical faces are of the same color? So don't be uh, excited or thrilled or tensed by the name probability here, because we are not using any probabilistic argument, okay? We're just using combinatorics, we're just counting. So essentially it's randomly, it means that it's randomly colored red or blue. So we are required to find the total number of cases where actually if you place a paint, you can actually find a position of the painted cube that can be placed on a horizontal surface such that the 4 vertical faces are of the same color. That's the question. Okay, you're from Belgium. Very good. So, okay, so I hope you understood the problem, Ilana. Ileane, I hope I understood the problem. So essentially, you are taking a cube, you're coloring it either red or blue, each of the faces. Now you're placing it on a, you're placing it on the surface, okay? And I mean, not randomly. What you're doing is that I'm just taking the cube and just placing it. I'm seeing which face is there, okay? Which face is really plausible. So that the four vertical faces are set the same color, okay? We're trying to do that. So let's try to understand the problem solution. Um, so this is suggested by one of your friends, and that is Sauradip, and he told this way. So he told us that let's consider number of colors, that number of faces of the same color. Okay. So observe one, Iliane, that if we color the faces three, I mean if we color the six faces, three and three different colors, okay, three blue and three red, then observe it is not never possible to find such a configuration, okay? So we are leaving that. So therefore there is only three possible choices: six faces of the same color, five faces of the same color, and four faces of the same color. Now if you color say all the six faces the same, obviously there's an arrangement like that, such four verticals are equally colored, same colored. So that is, we are choosing the six faces, and six choose six into two colors are possible, so 2 into 2, that is 2. Now five color faces same color, and therefore we have to choose five faces out of the six faces, and we are multiplying by 2, and it turns out to be 12 such possible arrangements of colors. And now four faces of the same colors, Liane, and now observe that four of the same colors will not actually suffice it, because we need to have four vertical faces of the same color, right? And it's not really possible always. So therefore what we do is coloring the four vertical faces the same color is same as coloring the rest of the two opposite vertical opposite and opposite faces of the same color, right? Coloring four vertical faces the same color is same as coloring two opposite faces as same color, okay, because it will fix the other. Therefore we are selecting all the possible pairs of opposite such possible pairs, right? And we therefore for three such possible pairs are there, and for each of the three possible pairs we have two colors possible, right? The red or blue, so therefore 3 times 2, therefore we get 6. So therefore total number of possible such colors, possible such arrangements are 6. 2 plus 12 plus 6, that is 20, and total number of possible arrangements for all the color arrangements possible is 2 to the power 6. So therefore what we get, 20 by 2 to the power 6, therefore you'll only get 5 by 16. Okay. No, Tishika, understand this. Okay, first of all, Linear, I hope you understood the solution. Now, Tishika, for Tishika, I'm telling this. See, try to understand this, Tishika. That you're coloring the four vertical faces the same, right? Exactly four vertical faces same. Because that's only when you will get that required arrangement, right? So therefore, coloring four vertical. Now imagine the cube in your mind's eye. Four vertical faces same color, that is same as equivalent to coloring exactly same color, and only four vertical faces are same color. That is equivalent to saying that the other two opposite faces, consider the four vertical faces, and other two opposite faces must be the other color and same color, right? Suppose the four vertical faces are red, the other two opposite faces must be blue. Or suppose the four vertical faces are blue, the other two opposite faces must be red. So therefore, it's selecting the four vertical faces same color is same as selecting the two opposite faces as same color, right? So now if you select and color the two opposite faces pairs, so which is sort of, I mean, two opposite faces pairs, and if you color it red or blue, and there are three such possible pairs, right? So therefore, three into two for two colors. Yeah, Aap and Kokinan, I will surely discuss IMO shortlist after the IOQM ends. Okay, it's an Indian Olympiad and it's easier problem. So may I know which standard you're in? This is a bit easier problem, I understand, surely. If you want us to solve IMO shortlist problems, I can surely do it. But maybe after our IQM ends, okay, because people may hard it and get demotivated. But thanks for letting us know what you really want. Ilyana and Tishika, I hope you understood. Dhruv, surely I will see to it, but can you send it to me in WhatsApp or Skype after the class? Okay, can I move to the next problem, guys? I am receiving the problem a bit late, and I'm so sorry for that. But yeah, let me know about your choices. Okay, my pleasure. May I move on to the next problem, guys? Okay, I will give my number to you. Or you can ask it from Sorodip, he has my number. Okay, so let's move on to the next problem, guys. Uh, the next problem is again a polynomial one. It's again a counting one, I guess. The polynomial, it's sort of asking the polynomial x cube minus 204, 2204, 2004, I'm so sorry, 2004 x square plus mx plus n has integer coefficients and 3 distinct positive zeros. Interesting. And exactly one of them is an integer and it's a sum of the other two. Okay. Okay. So the three positive distinct roots are one of them is an integer and it is a sum of the other two. Okay. It's r and r1 r is equal to r1 plus r2 and r1 r2. Okay, that's the idea. So how many values are possible for n? Okay, that's an interesting problem. Let's see. That's an interesting problem. I love this problem, I guess. Okay, so x is cube. So let's see this problem again. The polynomial x is cube minus 2004 x square plus mx plus n has integer coefficients and 3 positive distinct zeros. Okay. So how will you approach this problem? And one of them is an integer and it's a sum of the other two. So how many possible values of n are possible? How many values of n are really possible? Okay, so okay, I will approach you. I will help you to approach this problem. So now think about this, guys. So do you know about that rational root theorem that an integer is a root if and only if an integer is the divisor of that integer is the divisor of this n. Integer must be a divisor of this n. So how can you do that? What do you think about it? First of all, can you tell me what is it's really easy, like focus on this two numbers, 2 0 this one and n. Try to understand it now. It's really easy. Perfect. Very good, Tanay. Hi, Ravinder Sharma. Perfect. So essentially that's the idea. So observe, I will write down this whole thing now. It's x cube minus 2004 x square plus mx plus n is equal to 0 And observe that by Veda's formula again. So you see Veda's formula holds a really important role in these small problems. Okay, so be accustomed with it. So the sum of the roots is equal to 2004, right? Sum of the roots is equal to 2004. Observe, remember one thing, that one root, let r be the integer root, and r is equal to r1 plus r2 say. So therefore sum of the roots is what? R plus r1 plus r2. You can write it as 2r, which is equal to 2004. Therefore what do we get? The integer root is 1002, right? The integer root is 1002. Now do you know that if r is an integer root, then r must divide n? Do you know this result, guys? Otherwise I will prove it in front of you. Do you know this result, guys? If r is an integer root of this equation, then r must divide n. Why? Just put it x in this, so it's x is r cube minus 20404x r square plus mr is equal to minus n, right? Since r is a root. Now observe that r divides left hand side, therefore r divides right hand side. So therefore r must divide n. Sure. Veda's formula is the following. Okay. Um, I will give you Ilyane. I don't know whether are you a student of Cheenta, Ilyane? I mean, I can give you in Skype. You can search Veda's formula. I will try to explain it. It's very simple. So it's x minus x. R1 is the, if R1, R2, R3 are the roots, and if you expand it in terms of x cube minus ax square plus bx minus c, then you will see that if you just expand it now, you will get x cube minus r1 plus r2 plus r3 x square, plus r1 r2 plus r2 r3 plus r1 r3 x minus r1 r2 r3. So therefore you get that the coefficient A is same as R1 plus R2 plus R3. And similarly you can get all of them, each one of them, or everything out here, the relationships and between them. Okay, that's the essential idea, or the coefficients and the roots. So therefore that is the idea, that this the relation of the coefficient and the roots is actually called the Vieta's formula. Okay, Iyane? So now if you see this, then observe that the sum of the roots r1 plus r2 plus r3 is equal to 2004, and r is the integer root, and r1 plus r2 is equal to r1 plus r2, and therefore the sum of the roots is equal to twice r. So therefore twice r is equal to 2004 by this Vieta's formula, because this coefficient is same as r1 plus r2 plus r3, right? That is 2004 is equal to sum of the roots, which is equal to twice r. So therefore we get the integer root is 1002. And observe, by this result you get that the integer root must divide this n. So therefore what do we get? 1002 must divide n, right? So what's next? What do we do next? There is simply a notation, but I am not going to use that in summation formula. It will confuse the people over here. There are varied amount of people over here, no? So I cannot really, I don't want to take the responsibility of confusing them out. I mean, obviously they are learning something new, so also it's the duty of the seniors out here not to tell hard stuff to confuse the juniors. You must inspire people by simple stuff. Okay, so let's see. So what do we get over here? N is, oh no, n is given, no? N is I think n is given to be integer. No, given its integer coefficient. See, integer coefficient. So n is an integer, and you know that 1002 must divide n. So what do you get from here? How many values of n are possible? Think about it now. I've given enough hint to you. So I think we need to do a little bit more, okay? So let's try to do it from the basics again. So x minus r is a root, and x minus not r, say r1, r2. X minus r2 is a root, and then do it x minus, the other root is x minus r1 plus r2, right? So let's expand this, guys. So you get x cube is equal to 0. X cube minus r1 plus r2 plus r3 x square plus r1 r2 plus r1 r1 plus r2 plus r2 r1 plus r2, you know, times x minus r1 r2 r1 plus r2. This is equal to 0, and we know this is same as what? This is same as x cube. It is same as x cube minus 2004. Sorry, what I'm writing over here. I'm so sorry. Twice r1 r2 it will be, and therefore we'll be writing here plus mx minus plus n, I guess, or minus n is what is, I forgot it. Is it minus n or plus n? Um, um, um. Yeah, so therefore what do we get from here? Get that r1 plus r2 is equal to 1002. Okay, so replace it over here. So what do we get? It's x cube minus 2004 x square plus m. It becomes r1 r2 plus r1 plus r2 whole square. You see here, that is 1002 whole square. It becomes r1 plus r2 whole square. See here on this one. This one becomes r1 plus r2 whole square. So therefore it turns out that it's equal to 1002 whole square. X minus r1 r2 times 1002, okay, is equal to 0. So therefore what do we get? We get that m equal to r1 r2 plus 1002 whole square, r1 plus r2 is equal to 1002, and r1 r2 1002 r1 r2 is equal to n. This is the thing we are getting. So what do we get from here? What exactly do we get from here? Therefore we get that 1002 times 1002 whole square minus m is equal to n, right? This is the result we are getting. Therefore this is the thing we are getting, right? So therefore we can sort of understand from here what can be the possible m is what. Can you just check again? Let's check the question again. M must be positive, right? Why? Because these are distinct positive zeros. M must be positive. M must be positive, right? Because m is equal to sum of all this. So it's distinct positive zeros. R1, R2 is positive. So m must be positive. So that means what? That means, what are the possibilities of n? Just try to find it out. Are you sure about it? Think about it now. Think about it. Think about it. What are the possible values? N is positive. Yeah, positive roots. N is positive. Just think about it. Have I done it correctly? Is there any other restrictions on R1, R2? Is there any other restrictions on M? So what do you think? Is there any other restrictions on R1 plus R2 and R1, R2? Okay. What do you think, other people? What do you think? What do you think, guys? What are the Okay, why do you think so, Sarthak? Why do you think so? Okay, maybe. But see, observe it very carefully. Do you need some extra conditions on M? Can M be equal to 1? Because R1 and R2 are positive. Now R1 plus R2 is equal to 102, 1002. Can M be equal to 1? Can M be equal to 1? That's the question. So using R1 plus R2 is equal to 1002 and M is equal to, yeah, M must be having some conditions, you understand, right? So try to find the condition of M. When M can be equal to 1? When M can be equal to 0 rather? Can M be equal to 0? No. M must be equal to 1000, more than 1002. Is it? I think, sorry, it will be sorry. I'm so sorry. I made some mistake over here, some silly mistakes. It will be M minus that. M minus 1002 whole square. So you see, now you see an upper bound over here. So therefore, M must be having some such. I mean, now you can see it's an upper bound. M must be it must be having some upper bound. You understand? So what is the upper bound of M possible? Yeah, R and R2 are positive, right? But what can be there? What can be there? Can you just find out something? What can be there for R1? So let's see this problem now. So N is therefore, so understand, number of possible values of N is same as number of possible values of M greater than 1002 whole square. Okay, that's the idea, right? We have done. Number of possibilities of N is same as number of possibilities of M more than 1002 whole square. Now let's write down the only M wala equation. M is equal to what? 1002 whole square minus plus R1 R2, right? Now R1 plus R2 is what? Is 1002, right? So can you find an upper bound of R1 R2? Can you find an upper bound of R1 R2? Because that will give an upper bound of M, right? Can you find an upper bound of R2? Find an upper bound of R1 R2. It's very simple, guys. All of you know it. Yeah, you're right, Ilyane. It's like bijection, you're right. So if create a bijection between N and the M, you're right, totally right. Exactly. Number of values of M is actually equal to number of values of N, you're right. Perfect. Very good. Which standard you're in, Ilyane? Yes, so what's guys? How will you get it, guys? So try to understand this. So tell me, how do you get an upper bound from this? It's very easy, guys. You know, all of you know this. How will you get an upper bound of R1 R2 from R1 plus R2? This is a famous inequality, guys. Think about it. So see, we have to therefore find an upper bound of M, right? M has a lower bound, that is 1002 whole square. Now we need to have an upper bound. Perfect. Okay, hi, nice, Ilyane. Okay. Oh, very good, Ilyane. That's very inspiring. Okay. Yes, you're right, Shubham. AMG inequality, perfect. So use AMG inequality to find an upper bound. And R1 plus R2 whole square is what? You know, R1 plus R2 whole square is greater than equal to R1 square plus R2 square plus twice R1 R2. AMG inequality, this is greater than equal to twice R1 R2. So it's greater than equal to 4 R1 R2. So therefore 102 whole square is greater than equal to 4 R1 R2. Therefore we get that R1 R2 is less than equal to what? 5001 whole square. Perfect. And therefore R1 R2 plus what? R1 R2 plus square is less than equal to and greater than equal to 0, and therefore this implies that M is greater than equal to 1002 whole square and greater than actually 1002 whole square plus 5001 whole square, that is 25, I guess it's 25001. I am not sure about this. Let's see, it's around 25. I may be wrong actually, no. 25101 yeah, perfect, like this. Yes 25101, it's less than actually, you know. So therefore what do we get? We get that it can only take values. Now think about this, what we can do. Oh really, that's a condition in Turkey, right? Rajvardhan, please ping me in Skype. I've added to the superstars group. Please ping me in Skype. It's please ping me in WhatsApp. I'm so sorry. Okay, so did you understand this, guys? Any doubts? Yes. Did you understand how to approach this problem, guys? Any doubts from your end? Let's find out how to solve this problem. Okay. So, any doubts? Otherwise, I will wrap it up here. Any doubts? No doubts, I guess. Yes, without H. H is a little bit of upper wala stuff. Yep. Now it's perfectly correct. I know Google is there. Okay, so yeah, it was really nice talking to you. I have two new friends. You have two new friends over here, one from Turkey and another from Belgium. So very good. I hope you enjoyed it, guys, and let's see you in the next video, next seminar. And I hope you understood this and you enjoy this and see with newer problems, and I'll try to make harder problems for you cooking. Okay, bye bye, and see you guys in the next video. Bye bye. Next seminar is on the Thursday, same time. Perfect. See ya. Yes, the upper bound should be that. Perfect. But here we are interested in finding number of such cases,